what we're looking at today are predicting products. So we're going to focus on predicting products for single replacement and double replacement reactions, because those are the only two types of reactions that you'll be asked to predict the products, as you'll see in your Lab 9, the chemicals reaction lab. So this is a supplemental to Lab 9 to help you get through the pre-lab and then figure out how to predict the products of the reactions given in the other video where I'm mixing the chemicals together. All right, so here's the basic outline of a single replacement reaction. So we have an element by itself, represented by the letter A here, and it's reacting, so this is the reactant side of the equation. That element by itself is reacting with a compound, an ionic compound. Okay? What's happening, since it's a single replacement reaction, is this element A by itself is going to replace one of the elements in the compound, so that this element A is no longer by itself on the product side. On the product side, A is now part of the compound, and B is an element by itself. Okay, so we need to be able to predict what exactly is happening there. So we're going to just focus on this one and predict some products. So if I am given this chemical reaction here, I got magnesium and I'm adding HCl to it. Okay, so how do I tell this is a single replacement reaction? Because of the scheme over here. I have an element by itself, magnesium. Okay, so that's my A. And then I have a compound, so that's my BC portion. So H being my B, and chlorine being my C. So this is a single replacement because I have an element by itself reacting with a compound. So what I expect to happen to predict my products, I expect magnesium on the product side to be in a compound. So it's going to take the place of either hydrogen or chlorine. And then I expect either hydrogen or chlorine to be by itself. Okay, so how do you know what's happening? How do you know what the products are going to look like? Because remember, new products mean new subscripts. Okay, so what that means is we can't carry any subscripts that are here over. We need to figure out the charges on all the elements present, and then when they switch partners, what they're going to look like. So once I figure out the type, so first step, type of reaction, single replacement. Then I'm going to write down every element present and what its charge is according to the periodic table. Okay, so remember when we look at our periodic table, we can figure out the charge of the main group elements depending upon which group it's in. Okay, so magnesium is an alkaline earth metal. It's in group 2. So I have magnesium, and when it's in a compound, it's a +2. Okay, when it's by itself, it is neutral, but we need to know what its charge will be when it's in a compound, because on the product side, it's going to be in a compound. All right, now let's look for hydrogen. So what is hydrogen's charge? It's in group 1. It's not a metal, but it's still +1 like all the other metals in group 1. Okay, now finding chlorine, it's a halogen in group 17. So it is going to be a -1. So how do we know who's going to switch with who? Okay, well, whenever we have compounds, ionic compounds, we always want a cation, a positive charge, with an anion. So what that means is magnesium, since it has a plus charge, it's going to take the place of hydrogen since hydrogen has the plus charge. Okay, so magnesium and hydrogen are going to switch places. So magnesium is going to be with chlorine. So let me write that over here. So I'm going to have magnesium now with chlorine, because I need a positive with a negative. Remember, opposites attract. So that's why it's going to be a magnesium with chlorine and not magnesium with hydrogen. Okay, that won't happen. And then a hydrogen is going to be by itself. So let's start by predicting. So this was my A, right? Magnesium's my A, and then chlorine was my C. So notice I'm still following the pattern. I have A and C together in a compound now. But since it's a new product, we need new subscripts. Okay, so we need to figure out what the subscripts are going to be. And we did this in chapter 3, right? We used the charges, that crisscross method, to figure out what this compound would look like. So we took the 2 and made it a subscript on the opposite element. This 1 is going to make a subscript on magnesium. So what the product is going to look like is it's going to say that we need 1 magnesium and 2 chlorines. So MgCl2. So that is one product. What is my other product going to look like? Well, I just have a H. Now, is H stable by itself? It is not. We talked briefly about this in class. So there are certain nonmetals, and I have them highlighted in green here on this periodic table, that always form diatomics in nature, because this hydrogen atom by itself, it is not stable. Okay, so it pairs up with another hydrogen atom to become H2. Okay, so H2 is the other product. So what I'm going to write down here is the list of diatomics, if you can't see my periodic table. So hydrogen, you will never see by itself. It's always going to be H2. Nitrogen, N2. Oxygen will always be O2. It'll never be just one oxygen atom sitting alone. It's not stable that way. Then we have fluorine, F2. Chlorine, Cl2. Bromine, Br2, and then iodine, I2. You'll remember seeing iodine in the molecular geometry lab. When it said iodine gas, it was I2 because it exists as a diatomic in nature. So these are 7 elements that always appear as a diatomic in nature. Okay, and notice on the periodic table, hydrogen's included in that 7. And then to figure out the rest, you actually make a number 7, starting at nitrogen and going down to iodine. Okay, so that's how we know it's H2, is because hydrogen is a diatomic in nature. It's just more stable that way. All right, let's try another one. Okay. Now notice this isn't balanced, okay? So that's not the correct balanced chemical formula yet. I'm just focusing on predicting products right now. All right, so this will be B. Got there. So let's try another one. So this time we're going to do Br2 plus Ki. And then let's predict what the products are going to be. Okay? So, let's make sure we can see that, okay? Bromine is the element by itself. Okay, so bromine is our A. All right? Ki is our compound because it has 2 different elements combined. Okay, remember bromine was one of those diatomics that made that number 7 on the periodic table that has to be a diatomic in nature. That's why it's Br2 and not just bromine by itself. Okay, so bromine is our element by itself. That is our A. Then potassium iodide is our Bc. Okay, so before we predict the products, we need to figure out who's switching with who. Okay, so in order to do that, we need to know the charges so that we're making sure in the products that we have opposite charges making the compound, because opposite charges attract. So we need a positive and a negative combining to form the compound in the product. So if bromine's by itself, okay, what is its charge? It's a halogen, group 17, so it's going to be a -1 if it's in a compound. Looking at potassium, alkali metal, group 1, so it's going to be a +1. And then we have iodine, is a -1 because it is a halogen as well. Okay, so in this case, who is switching places? So it's going to be bromine and iodine who are switching places because they're both negatively charged. So they have the same charge, so they're the ones that are going to switch. So that means potassium is going to be with bromine on the product side, and iodine is now going to be that element by itself. So let's look in right over here on the product side what that looks like. And we're going to include the charges because the charges are going to tell us what the formula should look like. Okay, so we just said potassium with a +1. On the product side, it's not going to be with iodine anymore. It's now going to be with bromine because we need a positive and a negative together because opposites attract. That means that iodine is the only element left, so it is going to be by its lonesome. Now, is it going to be just one iodine atom sitting there by itself? Well, if you notice, it's highlighted in that number 7. It was one of those elements that forms a diatomic in nature. So it's not going to be I by itself. The final product is actually going to be I2. Okay, it's still an element by itself though, because both of those two atoms are of the same element. Okay, and I want to point out something here. Notice over here, there's just one iodine, right? No number present, so it's just one. Over here we have 2. Okay, that's because new products mean new subscripts. That's what that means. It means you're not just following these numbers over, you're figuring out what the number should be based off of charges, based off of if that element should be a diatomic or not. All right, so KBr, what is that going to look like when we combine it? So to figure that out, we do the crisscross method or we look at the charges. +1, -1, do those charges cancel each other out? They do. So all that means is we need 1 potassium and 1 bromine. So the final product is going to be KBr. Okay, plus here. So these are our predicted products right here, based off of the charges. Now this is not balanced yet. Okay, if you wanted it to be balanced, I could do that quickly. You would need to put a 2 here and a 2 here. Now it's balanced. Okay, so from the original problem, let me erase this bottom part. If it asked you to predict the products and balance the equation, this would be your final answer. And that's what you're doing essentially for the pre-lab, is you're going to be predicting products of the single and double replacement reactions, and then they're going to want you to balance as well. Okay. All right. Let's try some double replacement reactions. So looking at this scheme over here. So for double replacement reactions, so let me go back over here real quick. I have a slightly different scheme. So it's different than single, because single had an element by itself reacting with a compound, that element by itself switching places, so on the product side it's not by itself, and then another element that was originally in a compound by itself. Okay, so for double replacement, notice no elements by themselves. We have 2 compounds reacting, switching partners, so think of like dancing and you're switching partners to form 2 new compounds, 2 new sets of partners. So the reason I wrote the scheme down here again is I want to write the charges of each of these, because these are usually 2 ionic compounds reacting and switching partners. So my A is going to be positive, my B negative, because whenever we have a compound, an ionic compound, it's always a positively charged with a negatively charged, because opposites attract. Notice the positively charged ion is always first. Same when we named ionic compounds, we always named the positive, the metal portion first. So you always want the metal, the positive portion first. For CD, it's going to be the same. Positive first, negative next. Over here, positive, negative, positive, negative. Notice each pair has 1 positive and 1 negative. Okay, so let's draw a scheme here. wonder if I have enough room. Actually, I'm going to erase this just so I have more room to work the problem, since we're focusing on double right now. So we have copper sulfate. Actually, I'm going to need more room. Sorry. Barium chloride. All right, so given this reaction, if I ask you to predict the products, the first thing you want to do is identify the type, because that's going to help you figure out what's happening, who's switching with who. Okay, so notice I have two compounds reacting together, so it is double replacement. There's no elements by themselves. So they're going to switch partners. So we need to figure out who's switching with who. In order to figure that out, we need to know who's our A, who's our B, our C, our D, etc. Who's positively charged, who's negatively charged, all that good stuff. Okay, so I'm going to color code this to kind of make our lives easier. So we have copper. Now copper is a transition metal. So when I say transition metal, I'm talking about in this D block right here, right? So those metals, they are positively charged, but we don't know what their charge is. It could be a +1 or a +2, okay? So we don't know that yet, but we do know it's A because it is going to be positive. So I'm just going to put a question mark here because we're going to need to figure out what the charge on that copper is in order to figure out the products, okay? And we've done this before, so it'll be a little bit of a review. Now as for the B portion, so the other half of that compound, that is going to be this entire polyatomic. Okay, so SO4 is the B portion. Now the charge on SO4 we can figure out by looking at the polyatomic table, and it's actually a -2. Now the second compound, because I don't need this positive sign here, we have barium and chlorine. So we're going to write barium first, since it's the first one present, it's the metal, and you can figure that out by looking at the periodic table. It's in group 2. It's an alkaline earth metal. Did I say that wrong? Yeah, no, it's alkaline earth metal. So it's going to be, so barium is going to be positive because it's a metal, but more specifically +2. So I got that from the periodic table. And it's with chlorine, and you can guess chlorine's going to have to be negative because we always have a positive and a negative partner together. And since it's a halogen, it's actually -1. All right? So we need to switch partners. Who's switching with who? Okay? Well, in the end, we always want, for a compound, for a positive and a negative to be together. So copper is positive. We don't know positive what yet. But instead of being with sulfate on the product side, it's going to be with either barium or chlorine. Can copper be with barium? Will that make a good compound? It will not, because they're both positively charged. Positive charges don't like each other. So copper is going to take the place of barium and be with chlorine on the product side. Okay, so we're going to have copper, and we're going to figure out the charge on it in a minute, is going to be with chlorine. Okay, so that leaves barium and the sulfate ion. So with barium and the sulfate ion, which one, they're obviously going to be together because they're the only two left, but which one's going to be first? Are we going to put barium first or sulfate? We're going to put the barium one first because the metal, the positively charged ion, is always listed first, and then the non-metal portion. Need a bigger board, a bigger camera. All right, so we need to figure out on the product side what these products are going to look like. But in order to do that, we need to figure out what copper is going to be. What is the charge on copper? So to figure out the charge on copper, we look at the reactant side only. The reactant side will tell us what the charge on copper is, and whatever the charge on copper is on the reactant side, it's going to be the same charge over here on the product side. So I'm focusing on just this copper sulfate. Okay? For copper sulfate, to figure out the charge on copper, we look at the anion portion. The anion portion is a -2. This compound overall has to be neutral. So what does copper have to be to cancel out that -2 charge? It's going to have to be a positive 2 because a positive 2 and a negative 2 will make that compound overall neutral. So this is, remember naming, so we're going back to naming, copper 2, because with transition metals we always represent the charge with the Roman numeral, sulfate. Okay, since it's a +2 on the reactant side, the copper over here also has to be a +2. We're not changing what type of copper we're using in the reaction. If it's a +2 on the reactant, it's a +2 on the product. Okay, so now that you know the charges on all of these ions, you can figure out what the products should look like by doing the crisscross method. So for copper 2 chloride, it's got a +2 charge, so we're doing crisscross, so that 2 is going to become a subscript on chlorine, and this 1 is going to become a subscript on copper. So what we're going to have for one of our products is copper 1, chlorine 2, because we need 2 negative charges to cancel out that +2 charge. Our next product is going to be barium sulfate. Now look at the charges before you crisscross them. We have a +2 and a -2. Do they cancel each other out? Yes, they do. So that means we just need 1 barium and 1 sulfate. So these are our correct products. And actually, it's already balanced too. 1 copper on both sides, 1 sulfate on both sides, 1 barium on both sides, and 2 chlorines on both sides. It's a nice thing about double replacement reactions. They usually balance pretty nicely. Let me move this up a little, and I'm going to try another one down here. So let's try one. Might help a lot with lab here. PbNO3, and we do have a sub 2 on the outside, so that's going to be important. And we're adding potassium chromate to it. All right. So, predict the products. This is actually one from your pre-lab. So if you have to predict the products given just these 2 reactants, you need to figure out first what type. So we have 2 compounds reacting, so it is a double replacement. Okay, so now let's label it. So Pb is going to be my A, because Pb is a metal, so it is going to be positive. It is a transition metal too, so we're going to have to figure out that charge, much like we did with copper in the previous one. So I'm going to do a question mark for its charge. I know it's positive, but positive what is the question? Now for B. B is that what's in parentheses, that entire polyatomic. So it's going to be NO3 is your B. Okay. And then over here, K, or potassium, is going to be your C. How do I know that? Potassium is a metal, it's got a positive charge. More specifically, it has a positive 1 charge. It's an alkali metal. I forgot something over here with NO3. What's the charge on NO3? We know it should be negative based off of this schematics over here, but if you look at your polyatomic table, it's actually -1. So it's important to write the charges because when we switch partners, those charges are going to help us figure out what our new products look like. Okay, now what is our D? So our D is actually the rest of it. If you look at your polyatomic table, CrO4 is a polyatomic on that table. So that entire formula, CrO4, is the D portion. Okay? And its charge, if you look at the polyatomic table, is -2. So we have a positive something, we're going to figure that out with a negative, making 1 compound, positive with a negative, making another compound. Okay, so now we need to switch partners. So when we switch partners, let's start with lead, Pb. So we know it's positive, but the positive question mark is what we don't know. So this positively charged cation isn't going to be with NO3 anymore. It's now either going to be with potassium or with the chromate ion. So which one is it going to want to be with? It's going to want to be with potassium? No, we don't want two positives together. So it's going to be with the chromate. It's -2. And look, that's following with our color scheme. We have orange with blue on the product side, right? Good. And then we have two left. We have potassium and we have nitrate. Which one is going to be first, the K or the NO3? So we always want the positive cation first, and then we'll do the NO3 second. All right, before we predict our products, we need to know what that lead is. In order to figure out what lead is, what the charge on lead is, we're looking at the reactant, okay? Because this compound, as written, is neutral. So to figure out its charge, we look at the charge on the compound next to it, and it's a -1. But we also need to take into account how many there are. So how many NO3s are there? Because up here, there's just one SO4. So that's why we could say, oh, that one SO4 is a -2, so copper must be a +2. But down here, we have more than one NO3. So I'm going to write both of them down here. So if I have two NO3s, what's my total charge on the negative side? It's going to be -2. So what does my lead have to be to cancel out that total negative charge? It's going to be +2. Because +2 -2 equals 0. It's neutral, right? So I'm going to put a +2 here. Whatever charge it is on the reactant side, it's going to maintain that charge over on the product side. Another way to look at this as well, if you don't want to write all this out, is the reverse crisscross. So this being the charge on lead. Okay, making 2 being the charge. So let's move to our product side and let's predict our products now that we know what all the charges should be. So we have lead +2, chromate -2. Do those charges cancel as they are? They do. So we have PbCrO4. So we need just one of each. Potassium and nitrate also cancel. A -1 and a +1 cancel out. So we just need one of each of those as well. All right, is this one balanced? I'm erasing stuff. It actually is not. So to balance it, see, one lead, good there. NO3, there's 2 of them. Over here, only one NO3. So I'm going to add a 2 here. That will give me 2 potassiums and 2 NO3s. 2 potassiums, 2 NO3s. Now it's balanced just by putting that 2. Double replacement reactions are very nice to balance. All right, so hopefully that helps with the lab trying to predict your single replacement and double replacement reactions. Make sure that you are balancing them as well. For the double replacement reactions, use your solubility tables. Double replacement reactions only, use your solubility tables to figure out which one of the products formed a solid. Before I leave you today, let's look at one more type of reaction that oftentimes you'll be asked to predict. It's a very common reaction. So for this one, predict products. So C3H8, what that is a hydrocarbon. In this reaction, it's also known as, or can be replaced with the word fuel. Because when you mix a hydrocarbon or fuel with oxygen, what type of reaction happens? It's going to be a combustion reaction. So this is one of the 5 types of reactions you need to know. So combustion. So with a combustion reaction, it's always a hydrocarbon with oxygen or fuel with oxygen. You always get the same 2 products. Every time you mix a hydrocarbon and oxygen, you are going to get water as one product and carbon dioxide as the other product. Okay? Balancing these reactions proves difficult, so it's going to take a lot of back and forth. Notice oxygen is O2 on the reactant side because it's one of those non-metals that make that 7 that needs to be a diatomic in nature. Okay, and then also when you're balancing, notice the oxygens are in 2 different places. Okay, so be aware of that as you're adding the numbers to it. That just takes some practice there. So double, single, and combustion reactions, you need to be able to predict the products. You need to be able to balance them. For synthesis and decomposition, you need to be able to recognize the type but not predict products. But you do need to be able to balance them as well. So let me know if you have any questions. I made this video because a lot of people had some extra questions on the lab, so I hope this helps. If you let me know, give me enough time to make a video, I can do some more problems on any of these topics.